In week 2, we'll expand our knowledge by exploring the basics of machining and shop safety by visiting the Autodesk Pier 9 in San Francisco, California with John Peros, Autodesk Technical Program Manager, and also visiting the Haas Factory Outlet, a division of the Phillips Corporation in Colfax, North Carolina, with me, Matt Perez. Haas Automation is one of the largest machine tool builders in the United States. Today we'll have access to several machines including a Haas VF3 SSYT mill and a Haas ST30Y lathe. This course can't replace hands-on training and practical knowledge at a physical machine, but there are some basics we should really cover before we dive into programming toolpaths. Topics like coordinate systems, work holding devices, tools, and types of cutting. After completing this week, you'll be able to identify types of milling machines, demonstrate proper tool selection, explain a work coordinate system, and describe work holdings. Let's explore machining basics. In this lesson, we'll be discussing common materials. After completing this lesson, you'll be able to identify different types of material, define stock, and summarize differences in material shapes.
All right, so when we talk about CNC machining, we're talking about making a finished part. Now, to get to a finished part, we have to start with some sort of material. That's what the term stock refers to. So when you hear the term stock thrown around in the shop, what we refer to is the starting point of the part that we want finished. Now, I've got a lot of different types of materials here and a lot of different shapes and sizes. These are all considered stock. So for instance, this piece of steel right here, this might be stock that we would use on a laser cutter or a water jet machine where we're doing strictly 2D cutting operations. This piece of wood that we see is stock for a CNC router table, something that would work in 3 axes and generally cuts wood or foam. Now, if we look at these two pieces of aluminum right here, these are both different sizes and shapes of stock that we would put on sort of a standard 3-axis CNC machine. And of course, I've got 2 pieces of round stock here, and these would typically be used in a lathe or a turning center. Now, when you're thinking about stock, there's some important considerations to keep in mind. The first is that the stock size needs to be larger than the finished size of your part. So if I look at this piece of stock, it's 2 1/4 inches by 2 1/4 inches by 3 inches long. That means that the part I make has to be smaller than those dimensions. The same thing goes for all the rest of this stock on the table. Now, stock comes in both certified and uncertified variations that will hold different tolerances, but for the most part, you're going to make the assumption that you have to remove some amount of material to get a perfectly dimensioned surface on your finished part. So keep that in mind when you're designing a part, because stock comes in various standard sizes. Stock can also be had in custom sizes. Custom sizes, whether you order them or you machine the part down yourself, are going to be more expensive. So if you can design your part to fit inside a piece of standard stock size, you're going to be a lot better off from a procurement perspective than you would be if you needed a custom stock size. So with aluminum, for instance, you'll find that you can get a lot of stock sizes in 1/4 inch increments. You're almost assured to get stock sizes in 1/2 inch increments. And depending on the material that you're looking at, those increments and those available sizes of stock will be different. So keep that in mind at the first stages of designing your part. Now, the other thing to understand about stock is something that we call machinability. So all of these different types of materials will have a different machinability level. And you can find machinability indexes on the internet to sort of help you understand the machinability of different types of materials. But for instance, wood is going to be softer than aluminum, which is going to be softer than steel. And so the machinability of those 3 materials is going to be very different, which means that I'm going to have to be less aggressive removing material from a piece of steel than I would be if I was removing material from a piece of wood. What you'll find is that even in the same family of materials, take aluminum for instance, there will be different machinability levels. So what we've got here is 6061 aluminum. 6061 aluminum comes in multiple grades depending on whether it was annealed or heat treated, and those grades are going to change its machinability. And then you'll find that even going from 6061 aluminum to 7075 aluminum will change the machinability of the material. So all of this is stuff that you need to keep in mind when you're initially designing your part to make sure that the part can be made properly on the equipment you have access to when you're done.
In this lesson, we'll discuss how to use T-slots and clamps. After completing this lesson, you'll be able to identify methods of holding stock on a machine and compare various methods for holding stock. When just learning how to program a part to be cut, it can be easy to forget about how it's held. If you aren't coming from a shop background, it can be even easier because you really won't know what's available. In this lesson, we'll be exploring fixturing and work holding options that aren't vices. All machine tables will have slots running along the x-axis for use with T-nuts. In most cases, these are used to hold down a vise, which we'll get to, but there will be times when a vise just isn't the right option. Stock might be too large for a vise, it might have complex geometry, or it just might prohibit the use of a vise in some other means. So we can talk about things like custom soft jaws or really any other type of fixturing, but we want to specifically talk about what we have here in the Haas factory outlet in Colfax, North Carolina. Here we have a Haas VF3 SSYT, which means it has an extended Y travel over the VF3 SS. The table in this mill will be similar to any mill you come across, so it's a great example. Let's say that we need to hold down this block and machine a few small features in the face, but sadly we don't have an extra vise available right now. Another option is to use a clamp set like this. We have T-slot, nuts, studs, nuts, step blocks, and clamps with a matching serration. We simply need to position the clamps in a location we aren't going to machine, set them up properly, and now we have a rigid connection between our stock and the machine. Through our course, we will be focusing on vices as well as fixturing for multi-axis setups, but I encourage you to look through the available clamping options such as wedge clamps, mighty bites, toggle clamps, or any other commercially available options when you are planning your next work holding. In this lesson, we'll cover some basic information about vices. After completing this lesson, you'll be able to describe the various parts of a vise and identify the height of stock in use of parallels. A vise is one of the most common ways to hold stock to be machined in a mill. There are many variations out there, but at the end of the day, they all do the same thing: hold your stock to be machined. Let's take a minute to talk about some parts of a vise and some basics surrounding the use and maintenance of them. The main parts we want to understand will be the fixed jaw, the floating jaw, and the screw and handle. We also want to talk a bit about parallels that get our stock to the correct height and stops that help us position the part accurately. When setting up a coordinate system in a machine, referred to commonly just as G54, we will generally reference the back left corner of the part as it sits against the fixed jaw. CNC machines can repeat toolpaths with great accuracy, but if it doesn't have a good reference, it really won't matter. Parallels are used to help provide a raised surface for stock to rest on so that a tool has adequate clearance to machine. And parallels come in different heights and styles, such as ones that snap into the jaws of a vise. We could also create custom soft jaws that will replace these hardened jaws and hold parts with complex shapes. The handle on the vise will move the sliding or floating jaw in to clamp our part. And now that we've seen and can identify the basics of a vise, let's move on to how a vise relates to a vertical CNC mill. In this lesson, we'll learn about vise squareness. After completing this lesson, you'll be able to describe the importance of vise squareness and identify the tools needed to properly align a vise to a machine. Vise setup is a critical step in the process of machining, whether you're working on a manual machine or a CNC one. It's important to ensure that the fixed jaw of our vise properly aligns with the x-axis of our machine. To do this, we can use a dial indicator and adjust the vise position while we jog the table back and forth. In this example, we already have a dial indicator attached to the head of the machine, and it's snugly held on one side with a bolt and loosely on the other side, so we can tap it with a dead blow hammer to make small adjustments. Take note of the orientation of the dial indicator stylus, as the position is important for accuracy, even though we're only looking for a relative measurement from side to side. We want to slowly jog the machine into place, ensuring the steps of the jog aren't too big. We don't want to damage the instrument, so we must be careful at this step. Once we've engaged the stylus on the dial indicator, we can turn the bezel to 0. This isn't strictly required, as we are looking for a relative measurement, but it does help visually. With the dial indicator closest to our snugged nut, we'll jog in the positive X position, watching the dial. When we get to the other side, let's note the measurement. Tap the vise and repeat the process. Once we have a 0 reading on both ends of the vise, we can snug the bolts and measure one more time. Now, as the machine moves in the X and Y directions, we can ensure the squareness of the vise matches the coordinate system of the machine.
In this lesson, we'll talk about some topics that cover CNC machine safety. After completing this lesson, you'll be able to recall the tools required to use and install a vise, and review safe work practices prior to machine operation.
Safety should never take a back seat to getting the job done. The machines that we work with on a daily basis are precise and powerful and do exactly what we tell them, but it's us that makes the mistake and overlooks key details in the shop. Stock can get dropped, we trip, chunks of material can get flung around in a mill, so it's important that we take the proper precautions when working around some of the heavy machinery. For PPE, or personal protective equipment, we have safety glasses for our eyes, hearing protection, and protective shoes. Your shop may have specific requirements for safety, so it's always important to follow your employer or shop guidelines, and be sure to add anything you need to keep yourself safe. In addition to things we need, let's talk about a few things that we don't. We want to be sure we aren't wearing jewelry. We want to make sure that we remove any rings or watches and bracelets, as these could be potential snag points that could get caught in a moving machine. While these CNC machines have enclosures, they can be set up to stop or slow down when the door is opened. We still want to reduce the chance of getting injured. We should also remove any additional items such as necklaces or earrings, and again, these are based on your shop requirements. We should also consider what we're wearing in the shop and around the machines. We want to make sure that we avoid big baggy clothes, as it's a good idea to have tighter fitting shirts and make sure they're tucked in. Long hair should always be secure and tied back, and while these guidelines are more applicable to manual machines such as a lathe or a knee mill, they are good general guidelines. With ourselves taken care of, there are some general rules around the shop that we want to make sure we follow. Not only is a clean shop more efficient, but it's also much safer. Make sure that your area is clean, the floor is dry and free from debris and liquids. Make sure your workbench is organized and that tools are properly secure and not left in the machine. Now, this is by no means a replacement for any safety training, but a guide so you can understand some considerations when working around these big machines.
In this lesson, we'll discuss how typical CNC mills move. After completing this lesson, you'll be able to discover the work coordinate system of a mill, identify axis orientation of a CNC mill, and explain positive versus negative directions.
So here we are at our Haas VF2SS. This is going to be a fairly typical 3-axis milling machine that you'll see in most shops. They'll vary in size and amount of travel, but they're all going to have generally the same functionality. So on a milling machine, what you have is a tool. That tool is going to spin, and that spinning tool is going to drive around a part and remove material to get you to your finished product. Now on these machines, we have a very specific work coordinate system that we refer to. You've probably seen the little axis in your CAD program that says X, Y, and Z. That X, Y, and Z very specifically refers to directions in this machine. Now, the X direction on a machine like this is going to be moving left to right. The Y direction on this machine is going to be moving back to front. and the Z direction on this machine will be the spindle or the tool coming up and down. As far as the negative versus positive directions go, what you'll find is that X positive is moving to the right, Y positive is moving back to the machine, and Z positive will be moving up. So currently this machine is as high as the Z will go. So that's all the way in the Z positive direction. Now, when you move the machine around, you'll find that it's not just the tool that moves, it's actually the bed that moves. So if we were to look at moving this in the X positive direction, you can see that the table is actually moving to the left. Now I said that X positive on this machine was to the right. And so what you want to keep in mind on a milling center like this where the table moves is that the positive direction is the way the tool moves in relationship to the bed. So even though the bed is moving to the left, that's actually positioning the tool further to the right on the table, and that is our X positive direction. The same thing goes for Y. So if we go into the Y positive direction, or I'm going to go in Y negative because I was already as far Y positive as I could go. So here we are a little Y negative. If we move back in the Y positive direction, you'll see that the table is moving towards me. And remember, Y positive is to the back of the machine, but by the table moving forward, we're actually putting the tool further back in the positive direction. Now the Z-axis is a little bit easier to think about because negative will be down and positive will be up. So here I'm moving in the Z negative direction, I'm coming closer to the part. Here I'm moving in the Z positive direction where I'm going further away from the part. One really cool trick that you can keep in mind when you're doing this in a CAD system is that XYZ equals RGB. So generally that triad, that coordinate system in your CAD system will be colored. The X-axis will be red, the Y-axis will be green, and the Z-axis will be indicated in blue. So when you're doing your programming and you see those colors, that's what they refer to. So another thing to think about when we're talking about our work holding is where in the machine the part is actually going to be. So right now the machine is at what the machine considers to be its home point, or 0, 0, 0 in the XYZ coordinate system. If I tell it to start machining from 0, 0, 0, it's going to be machining up here, way far away from my part. So what I need to do is tell the CNC machine where my part 0 is. And when you program in your CAM tool, you will choose a specific 0, 0, 0 position on your stock. I need to make that position match the position of the stock in the machine. To do that, a couple things need to happen. I need to move in the X negative direction a little bit. I need to move in the Z negative direction a little bit. And I need to move in the Y negative direction a little bit. In order to find that point, which maybe we could call the back left corner, I'm going to use a probing tool on my machine of some sort. And there are numerous types of probing tools that are available to you. But once I find that specific point, the machine will know the distance values in X, Y, and Z from its home location to the 0, 0 point of our stock. That is called my work offset. You'll often hear this referred to as G54, which is the nomenclature for capturing that point in space on the machine controller.
In this lesson, we'll talk about how typical CNC lathes move. After completing this lesson, you'll be able to discover the work coordinate system of a lathe, identify the differences between a lathe and a mill, and explain tool direction.
So now we're standing in front of our Haas ST10Y. This is a turning center or a lathe. The main difference between a lathe and a mill is that in the mill, the tool is spinning, and in a lathe, the material is spinning. As such, the layout of the axes in the lathe is a little bit different than what we talked about in the mill. So, what you'll see here is the lathe spindle. That's where we're going to put the material in, and the material will be spun around. That material is spinning around the C-axis. So if we remember from before, we talked about XYZ equals RGB in terms of axis colors. When we talk about rotational axes, we can remember XYZ equals ABC. So when we talk about the C-axis rotating, that C-axis will be rotating about the Z-axis. So in this machine, the Z-axis is the direction axially along the spindle. Now in your typical lathe, you're going to have the Z-axis and the X-axis. The X-axis is going to be the tools coming in towards the material. We can see here we've got a tool holder. In the case of this lathe, it's a turret with multiple tools loaded. And those tools will come down and they will approach the material from the top side. That is our X-axis. Now, this lathe being an ST10Y also means that it has a live Y-axis, which is not common on all lathes. What that allows us to do, instead of just basic turning operations, is to also use this lathe for milling operations, often referred to as a mill turn machine. Now the Y-axis in this case will be at 90 degrees to the X-axis. So if our X-axis is coming in towards the material this way, the Y-axis will move the tools in and out that way. You can see from a tool perspective that I have tools that are along the X-axis pointing at the material, and I have tools that are along the Z-axis pointing along the center line of the material. Those are traditionally the two types of tool orientations that you will see in a lathe. Now this machine having a live Y-axis means that some of these tools can actually spin. So if we were doing milling operations, the lathe would stop the material from spinning. It would then spin the tool and it would move it in X, Y, and Z as you would expect on a standard mill. That way I can get axially symmetric round parts, but I could mill flats or grooves or other things into them that are not axially symmetric. So much like we talked about on our milling machine, the machine itself has a home position, and then there's a zero position for the stock material that we often refer to as the work offset, or sometimes you'll hear that as G54. On a lathe, it's a little bit different than it is on the mill. So if you remember on the mill, we changed position in both X, Y, and Z to set our G54 on the stock. On a lathe, the only thing we need to change is our Z position. When you program a part for a lathe, you're going to set your part 0 to the center line of the material or the center line of the spindle. That will be X0, Y0. That doesn't need to change between the machine coordinate system and your part coordinate system. So all we have to do is move the machine in the Z direction to the face of our part, and we can set that as our Z0, and that will give us our G54.
In this lesson, we'll discuss the types of milling tools. After completing this lesson, you'll be able to describe roughing versus finishing tools, explain milling tools and their functions, identify types of tool holders, and identify types of tools.
Milling tools come in a wide variety of shapes, sizes, and coatings, and we can't cover them all, but we want to take a look at a few standard tools that you should know. First, we want to talk about the flat end mill. Flat end mills are used for both roughing and finishing operations and are able to produce square corners when milling pockets. There are many variations of these tools, such as roughing versus finishing, center versus non-center cutting, and tools with through coolant. There are other variations, such as the angle and number of cutting flutes. These parameters, as well as their material and surface coating, will dictate what material they should be used on and how fast they should spin and move when they're cutting. Next, we want to move on to the ball end mill. The ball end mill will have a full radius and is generally used for finishing of complex shapes. In between flat and ball is a tool called a bull end mill. This is very similar to a flat end mill, but has a small radius on the corner. These tools are great for a wide variety of applications because of their geometry and can be used to rough and finish pockets that have a radius, as well as cut complex 3D geometry. There are many other variations of tools such as pencil, lollipop, and chamfer to name a few. Each of those will have their own specific applications. Next, we want to talk about tools for facing, and these are for cutting the tops of parts. And again, there are many variations of these. Here we have an insert type facing tool. These tools are specifically designed for cutting the top of parts. The last thing that we want to discuss here for tools is going to be ones for hole making. To start holes, we have center and spot drills, then onto actual drill bits. And again, drill bits have various options such as materials, coatings, and coolant options such as through coolant. In addition to this, we have reams to help finish holes, and then we have taps to help cut or form threads in a pre-drilled hole. One more item that we do need to cover is the holder itself. Holders come in various tapers, types, and sizes, and we won't be covering these in general, but we want to make sure that we understand that the tool extends or projects from the holder. This will be important as it will affect how far the tool can reach into a part and the tool's overall stability. The farther a tool sticks out, especially a small diameter tool, the more chatter or vibration it will have and the less accurate or clean the cut will be. The main thing to understand is that various types of tools are used for various different applications. So we need to be familiar with these and be able to identify them as we begin to program our parts.
In this lesson, we'll discuss types of lathe tools. After completing this lesson, you'll be able to describe the difference between mill and lathe tools, identify tool shape and nomenclature, and identify types of tool holders.
Lathe tools, at least non-live lathe tools, have some distinct differences to milling tools. Let's take a look and understand some of the basics of lathe tools. First, there are 5 basic types of lathe tools. External tools, which can be used for roughing and finishing the outside of a part. Boring bars, which can be used to increase the inside diameter of a hole or finish internal geometry. Drills, which are the same ones that you would use on a mill or a drill press. Thread making tools, which include both rigid tapping tools as well as thread cutting tools. And finally, parting tools, which will be used to cut the part away from the rest of the stock. Parting tools can also be used for things like cutting geometry such as grooves. On top of that, tool holders or assemblies can come in 3 different orientations: right hand, left hand, and center or neutral. If you lay the tools on the table with the insert facing up, a right-handed tool will have the insert pointing to the left, and a left-handed tool will have the insert pointing to the right. The different orientations are used based on the geometry to cut as well as the cutter position. Many of these tools use an insert, and there are even more types of inserts. Inserts vary in size, shape, and coatings, but we won't be going through all the variations in this specialization. As we go through the course, we will be using some of the basic tools for various applications, so it's important we understand the basic types and orientations of these tools as we get started.